Hello everyone, this is Mr. Appel, and today we're going to look at inequalities in triangles, look at whether triangles can be formed given side lengths, and things you can determine about a triangle when you know some things about angles and sides. So to start, let's take a look at this problem. I'm going to read it to you in case you can't see it on the video. It says Michael drives to school from his house. Directly there, straight there, and he travels 6 miles. His friend Janet drives from their school to a store, straight to the store in some direction. She drives 2.5 miles on her trip. At most, how far is that store from Michael's house? And what is the closest the store could be? So this is kind of an interesting question to think about. I'd like you to pause here, try to sketch it, really try to think about how you would answer this question, and then come back and I'll show you. Okay, so if we assume that we've got Michael's school, so school is right here, and his house is over here somewhere, so it's exactly 6 miles from the school to the house. And Janet is going from that school 2.5 miles to get to the store. The sort of key to this is that she could be going in any direction. She could be going 2.5 miles this way, or this way, or this way, or this way. So if we're wondering how far is the same store from Michael's house, and what's the closest it could be, well, the closest it could be to his house would be if she had driven along that same route, so it had been right here. And then the furthest it could be would be if you'd gone the other direction, this way. So we're trying to figure out is what's the furthest it could possibly be and what's the closest it could possibly be. So if it went 2.5 miles away from the school in the opposite direction, you'd have 2.5 miles plus the 6 miles from the school to the house. They'd be 8.5 miles apart. But if the store was as close as possible, so in the same direction, then you'd have this 6 miles, and then you'd have this 2.5 miles, and what would be left would be this distance, which would be 3.5 miles. So it would have to be, they'd have to be more than 3.5 miles apart, or at most the closest, could be 3.5 miles apart, and the furthest apart they could be would be 8.5 miles. Okay, and that's the gist there. And that leads us to this theorem that says, given 3 side lengths, so if I give you any 3 side lengths, the sum of the 2 smaller ones must be greater than the longest in order for a triangle to be formed. Because remember, this is connecting back to that activity we did a little while ago, where those 2 examples I just gave don't actually form triangles because they make straight lines. So I'm going to show you just an example to illustrate that a little bit, show you this in another way in the Geometer Sketchpad. So here's the situation. There's the school, there's Michael's house, and you see there's 6, well, in this case centimeters, but we'll just pretend that's miles, so 6 miles apart. And again, the store, if it's as far away as it could possibly be, so in the opposite direction, it's 6 miles from the school to Michael's house, 2.5 miles in the other direction to the store, so they're 8.5 miles apart. But the point here that we're really interested in is that that can't form a triangle. There's no triangle there. But if it's just a little bit closer, now it does form a triangle. And so that longest side, if you add up the 2 shorter sides, the 2.5 plus the 6, has to add up to more than that side, which now it does. It doesn't here. They're equal, so it didn't make a triangle, but now it does. Because now this 8.5 is a little bigger than 8.4. If we move on the other side of things, now I'm looking at the 2 shortest sides of the triangle. So the 2 and the 2.5, and the 3.6 in this case do add up to more than 6, because 2.5 plus 3.6 is 6.1. But if they're right on that straight line, if they're exactly equal, so if the 2 shorter ones, 2.5 plus 3.5 equals 6, it doesn't make a triangle anymore. Okay, let's look at some examples to try to illustrate that. So if I gave you these three side lengths, so if I gave you 7, 10, and 12, the question is, can you make a triangle? And very simply, the two shorter ones are these. So the answer is going to be yes, and your reason would be because the two shorter ones, 7 plus 10, are more than 12. So if the two shorter ones add up to more than the longest one, you're good. If not, it's not a triangle. Here, the two shorter ones are D, E, and E, F. So 5 plus 6. How does that compare to 14? Is it greater than 14? It is not greater than 14. And so the answer there is no. And this would be enough to justify it. Okay, 8 plus 9. 8 and 9 are the two shorter ones here. How does that compare to 17? Or is it bigger than 17? Put a question mark there. Is it bigger? No, it's not. So if the answer is no, then it can't make a triangle. This is that situation we looked at before where the two shorter ones are just equal to the longest one, so you end up with a straight line and not a triangle. This last one, sort of a trick question, but not really. The two shorter ones would be any of the two 10s. The longest side would be also one of the 10s, so it doesn't really matter which ones you pick. And certainly 10 plus 10 is bigger than 10, so that satisfies our theorem. So this is yes, we can make a triangle. Of course, we know that's actually an equilateral triangle. Okay, moving on. I want to look at another sketch in Geometer Sketchpad to help show you something. So here's a triangle, and what we're interested in here is if I give you the side lengths of a triangle, can you predict anything about what the angle measures? And what I mean by that is which are going to be the longest ones, which are going to be the shortest ones. And we're just going to do this sort of informally. So I'm going to show those angle measures so you can see them. And you see this is an isosceles triangle right now because these two sides are equal. And of course the opposite angles are also equal. But let's see what happens if we change that up a little bit. Okay, let's say we make that really small. Well, notice now what I did is I made that vertex angle much bigger than the other two. All right, so that one's 150 to 3 degrees. The other ones are only 13. So now which side is biggest in that triangle? Well, AB is now bigger than the other two. And the angle opposite AB is now the biggest angle. And want to see when that happens. If you notice here, it's still true, it's still true, it's still true, still true, right? So as long as that vertex angle, that angle is bigger than the other two, the opposite side is bigger than the other two. But as soon as that angle goes the other way, so now this angle is smaller, that opposite side becomes smaller. And that's kind of the gist of what we're looking at here. So let's get back to our theorems. So these are kind of wordy. I'll give them to you in words there. You should probably have them written down. But basically what this says is, it says if one side of a triangle is longer than a second side, then the angle opposite the first side is larger than the angle opposite the second side. Wow, that's really confusing. A much better way to say that is when you have a triangle, I'm just going to give an example, not drawn to scale, whichever side is the longest, whichever side is the longest, the angle opposite that side is going to be the longest. So if this is 10, 9, and 8, and I ask you which angle, A, B, or C, is going to be the biggest angle is always going to be the one opposite the biggest side. So if the 10 is the biggest side, that means angle C is going to be the biggest angle. And if I ask you which one's the smallest angle, same thing. BC is the shortest side, so the angle opposite that is going to be the smallest angle. So angle A, the measure of angle A, is going to be smaller than the measure of angle B, and that's going to be smaller than the measure of angle C. Wow, that writing is really sloppy, but hopefully you heard what I said. And then this second theorem says basically the converse of that, which is that if you know the angles, so if this is 50, 60, and 70, again, not drawn to scale, that you can determine the longest side is going to be the one opposite the biggest angle, So the biggest angle is 70, so the longest side will be AB. And the shortest side is the one opposite the smallest angle, so that would be AC. So again, I know those are a little bit wordy, but that's the gist of it. Let's look at a couple examples, and then we'll be done. So here I've given you some angles. So in this case, I only know 2 of the angles, so I want to figure out the third. 70 and 75 is 145. That leaves 35 degrees for this one. So it asks you to name the largest side and the smallest side. Largest side is the one opposite the largest angle. So the largest side here is going to be segment BC. The smallest side is going to be the one opposite the smallest angle, so that's going to be AB. Over here, that's 43, that's 90. Add them up, subtract from 180, and I get 47. So the largest side is the one opposite the 90, which is going to be DF. And the smallest side is going to be the one opposite the smallest angle. That angle is 43. The opposite side is segment DE. And so segment DE is going to be the smallest side of that triangle. Then turning that around, same idea here. The largest angle is going to be the one opposite the largest side. So in this case, that's the largest side. So angle B will be the largest angle. In this one, the smallest side is 21. So the opposite angle there, C, will be the smallest angle. Hopefully you're getting the gist of this. Over here, biggest side is 14. So biggest angle is angle E. Smallest side is 9, so the smallest angle is the opposite angle, which is angle D. That's all. Good luck.